So guys, today we are going to deal with the topic solubility of liquid in a liquid. So basically, what does it mean? If you are taking a container, basically here your solvent will be also a liquid and the added solute will be also in the liquid. But the major tendency you have to remember that both the liquid forms here will be volatile and the system is in a closed container. So we are taking a binary solution, that means a solution which is having the two components and both the components are volatile in nature. So if I consider the liquid 1 as a component 1 and the another liquid as a component 2, let P total be the total pressure exerted by the two volatile liquids, since they have attained an equilibrium under this closed system. So if P total is the total pressure of the two volatile liquids, let us consider that P1 be the partial vapor pressure of a liquid or a component 1 and P2 be the partial vapor pressure of the component 2. If I consider that X1 be the mole fraction of that of the component 1 and the X2 be the mole fraction of the component 2, then all these parameters are related and they have been given with a mathematical expression using a Raoults law by a name given by a French chemist called as Raoult. So the expression he gives is that your P1 is directly proportional to X1. Similarly, your P2 is directly proportional to X2. So by seeing this mathematical expression, he gave us a statement which is called as Raoult's law of partial vapor pressure. He says that in a mixture of two volatile liquids or in a mixture of volatile liquids, the partial vapor pressure of each liquid, the partial vapor pressure of each component or a liquid, whatever, of a solution, so what they have said, partial vapor pressure of each component of a solution is directly proportional to its mole fraction present in the solution, That is the thing what we have written mathematically. So the major thing we have to add over here is in a mixture of volatile liquids. So the partial vapor pressure of each component of a solute, that is your P1, is directly proportional to its mole fraction present in the solution. So depending upon this one, as we have written earlier, so P1 is directly proportional to X1 for the component 1. Similarly, P2 is directly proportional to X2. So in order to remove this proportionality constant, what we are going to add? So in order to remove this proportionality sign, we are adding an proportionality constant, that P1 naught into X1. Similarly, P2 is equals to P2 naught into X2. This P1 naught and the P2 naught are the vapor pressures of the pure components. Now the question arises, what do you mean by this pure components? For example, if I am taking a system which is having that of your ethanol and that of your acetone. Of course, both are the volatile liquids. So this is comprising a solution. So in this solution, whatever the pressure I am going to calculate for individually within this mixture, that will be your P1 and P2. But when I am taking a system which has been closed and it is enclosing only ethanol and I am measuring its partial pressure above the surface of the liquid, that will be your P1 naught. That is the vapor pressure of your pure component. Similarly, in another system, if you are going to take your acetone in a closed system, remember, so that whatever the vapor pressure you are going to calculate, that will be your P2 naught. That is the reason we are saying that P1 naught and a P2 naught are the vapor pressures of the pure components. From the Dalton's law of partial vapor pressure, we can write as what? Your P total is equals to P1 plus P2. Yes, we know what? P1 is equals to P1 naught x1 and P2 is equals to P2 naught x2. Just substituting that one, P1 naught x1 plus P2 naught x2. So this will be your P total, and this is the mathematical expression for your Raoults law. But we also know that what? When you are adding, or when you are going to take the sum of the mole fractions of the two components, x1 plus x2 is equals to 1. So your x1 will be equals to what? 1 minus x2. So we can just substitute over here. So you're going to get as P1 naught into 1 minus x2 plus P2 naught into x2. So P1 naught minus of P1 naught x2 plus P2 naught x2. So P1 naught minus of, if you can just take it as what? Plus if I take what you can write over there then. So P2 naught minus P1 naught. So this can be also an expression for your Raoults law. So what you are saying basically over here is, basically if you can remember, it is a solubility of a liquid in a liquid. So whatever in a mixture of these volatile liquids, the partial pressure you are going to obtain will be directly proportional to its mole fraction. It is similar to that of your Henry's law. But in the Henry's law, what we have seen, it was the solubility of a gas in a liquid. But the expression we have obtained the same. If you are remembering, we have written over there as P1 is equals to KH into X. Where this is also your partial vapor pressure, this is your mole fraction. But the major difference between the Raoults law and that of your Henry's law is with respect to their constant. Here we are getting as a KH as a Henry constant, whereas here we are going to get that as a Raoults constant. So what you can say is, Raoults law is a special case of Henry's law. It's a special case of Henry's law. So what you can say, whatever the rate your Henry's constant is there, that will be equals to that of your P1 naught. So by this way we are able to explain the solubility of a liquid in a liquid by Raoults law. So coming with respect to the figure or the graph, of course we the same graph, but you have to remember that we are taken over here as a two components. If I am going to plot them individually, of course what I am going to get, so this is your mole fraction and this is your vapor pressure. So this is for x1 if I am going to calculate. Of course, as the vapor pressure is going on increasing, what happens to the mole fraction? It also goes on increases linearly. Similarly for the component 2 also I am going to get the same thing. Yes, this is your vapor pressure, here is your mole fraction. But when I am going to take both the graphs in a single way, of course I can write it in this way. That is, here if I consider that x1 is equals to 1 till x and x2 is equals to 0, the graph will be in this way. Linearly it is going. Here is your mole fraction, here is your vapor pressure. Similarly, when I consider over here as x2 is equals to 1 and x1 is equals to 0, the graph will be in this way. Here you could just notice that, so whatever the line you are getting over here, from here to here, so this is called as that of your P total. Now you can ask me, of course, so here whatever the point you are getting, here it is your P1 naught and here it is your P2 naught. Why P1 naught is less than P2 naught? Here we have assumed that whatever the component 1 you are taken, that is less volatile. If it is less volatile means what? The pressure is less, and that is the reason we have got as a minimum point. When you are considering to that of the component 2 or the second liquid, that is somewhat more volatile when compared to the liquid 1. So volatility is more means what? It will be exerting the maximum pressure, and that is the reason the pressure is more. So that is the reason we have got this graph, very much important in order to explain your Raoults law of evaporation graphically. So whatever the line you are joining from P1 naught to P2 naught, that will be giving your P total. Now the question arises that what is the use of this Raoults law? So basically whenever we are dealing with a machine, of course we say that a Carnot cycle which is having a 100% efficiency. Even though such a machine does not exist, that is we say it's an ideal machine. We are considering some other machines with respect to that machine. Similarly, when you're going with that of your gases, we also study with respect to the ideal gases. Of course, those gases does not exist, but whatever the gases we are drawing it, it is from that concept we are going to take it. Similarly, by using this Raoults law, we are going to see the two types of a solution. One is called as ideal solution and another is called as non-ideal solution. So first of all, we'll deal with what do you mean by this ideal solution. Remember guys, the solution which obeys the Raoults law at all conditions of your temperature and that of your concentration. So those solutions are called as what? Ideal solution. Of course, you can easily say now, what do you mean by this non-ideal solution? So solution that doesn't obeys Raoults law at all conditions of your temperature and concentration, that is called as your non-ideal solution. Of course, in this ideal solution, we can give an example. For example, I'm going to give a mixture of your benzene and toluene. This is your benzene. This is your toluene. So these can be taken. So this mixture can be taken as a source or an example of your ideal solution. Coming with respect to the characteristics of this ideal solution, how can you say that these two liquids are ideal? Basically, we are having certain characteristics. What are those characteristics? The first most important characteristic to say that the two solutions are ideal is that, so whatever you're going to calculate the P total experimentally, through experiment whatever you're calculating, the total pressure, that matches or that will be equal to the value which is you are calculating from the Raoults law, that is P1 naught x1 plus P2 naught x2. So that is the first characteristic. So experimentally determine the total vapor pressure of the two solution is equal to that of your value calculated from that of your Raoults law. And the second important characteristic to say that the two solutions are ideal, it is that the total volume of the solution, is equals to the sum of the volume of the two components present in this solution. Or in simple words, we can say that when you're taking the difference of that, delta V of mix is equals to 0. There is the total volume and the sum of this volume. When you're taking a difference of these two things, we are getting the delta V of mix is equals to 0. The third most important thing with respect to the temperature is they say that heat is neither absorbed nor it is released during the preparation of this ideal solution. The fourth most important point, because whatever the next concept we are going to see, it is mainly depends upon this point. That is, they are saying that solute and a solvent interaction is equal to the solute-solute interaction and solvent-solvent interaction. That is, for example, if I say that if your benzene is the solvent and your toluene is a solute. So whatever the interaction is seen between a benzene and that of the toluene is similar to that of the interaction of your benzene and a benzene, toluene and a toluene. So if these four characteristics are observed in a mixture of a two solution, such a solution will be called as that of your ideal solution. That is, whatever the experimentally total vapor pressure you are going to calculate, that should be equal to the Raoults law of partial vapor pressure. Secondly, they say is that the total volume of a solution should be equal to the sum of the volume of your individual components. Or in simple words, your delta V of the mixture should be equals to 0. Here they are saying the third point that heat is neither it is absorbed nor it is released. That is, we can say that delta H of the mixture should be equals to 0. Coming with respect to the fourth point, very much important, it says that here the solute-solvent interaction will be equals to solute-solute and a solvent-solvent interaction. So if these four characteristics is observed in a mixture of a two solution, such a solution will be called as ideal solution. Example is your benzene and toluene, your N-heptane and N-hexane, similarly your bromoethane. All these can be taken as an example for your ideal solutions. Of course, when you are seeing its graph, since it is following that of your Raoults law, the same graph will be observed. So this is for your x1 is equals to 1. Here it is your x2 is equals to 1. Here the x2 is equals to 0. Here the x1 is equals to 0. So this will be your graph. Same as that what we have done earlier, P total. Of course, this should be somewhat slant in this way, since P1 naught is less than that of your P2 naught. Okay, so this is your P1 and this is your P2. Same as that of your Raoults law. Coming with respect to the non-ideal solution, as we have said, the solution does not obey the Raoults law. Coming with respect to their examples, the major examples I would like to give, the common example is a mixture of your HCl and water. Of course, we have done this while diluting the HCl solution. So whatever you are doing over here, the mixture of HCl and H2, that is an example of a non-ideal solution. You can ask me, sir, how can we say that as two solutions are non-ideal? Coming with respect to their characteristics, it is just the vice versa of your ideal solution. That what does it say is, whatever the P total you are observed experimentally is not equal to that of the P total obtained from the Raoults law. So that is the first characteristic. Coming with respect to the second characteristic, the total volume of the solution is not equal to that of your sum of the volumes of the individual components of a solution, or in simple words, delta V of mixture is not equals to 0. The third point, here the heat can be absorbed or it can be also liberated during the preparation of the solution. That is, delta H of the mixture is not equals to 0. But the most important point we have to just remember over here once again, easily you can also say the solute-solvent. The solute-solvent interaction is not equal to that of your solute-solute interaction and solvent-solvent interaction. So if these characteristics is observed in a mixture of a two volatile liquids, such solutions will be called as that of your non-ideal solution. But in my next video, we are going to see the different types of a non-ideal solution.